Let's talk for a moment about symmetry in functions. I'll start with the real basic example. F of x equals x squared. This is a function that is symmetrical about the y-axis. And what I mean by that is if we were to graph it, x would be at the origin, 0. And this function would be symmetrical about the y-axis, meaning that the y-axis, in a certain sense, slices it in half. So we can fold one side over. There are lots of different functions about the y-axis. These functions are also known as even functions. And these functions have a really curious property. And to put it in words, if you use opposite input, you get the same output. And here's what I mean using our original example. For f of x, if f of 2 is equal to 2 squared, which is 4. And if I use the opposite input, negative 2 squared is also 4. So opposite inputs, 2 and negative 2, give the same outputs, 4 and 4. And this can be generalized a little bit, where we could say that f of x equals f of negative x, or in our previous case, f of 2 is equal to f of negative 2, because both cases give you 4. Now sometimes it's easy to tell if a function is even, just based on you're squaring a single number or things of that nature, or you happen to know what the graph looks like. But if you weren't sure, a way you could test it would look something like this. F of x equals x squared plus 4. If I wanted to show that this function is even, I would need to show that for any value I could choose for x, I'm always going to get the same output for both an input 2 and its opposite negative 2. I mean, another way to phrase the question is, if f of x equals x squared plus 4, what will happen if I were to substitute in the opposite of x? All right, so now I'm generalizing a procedure rather than using one specific thing, 2 and negative 2, or 3 and negative 3. I'm using x, and I'll get x squared plus 4, and the opposite of x. I'm testing everything and every opposite. And notice that by substitution, when I use the input negative x, if I square negative x, I will end up with x squared plus 4. And because f of x and f of negative x simplify down both to x squared plus 4, I have verified that this is an even function. It's symmetric about the y-axis. I know these as facts. Now there is a second kind of basic function. It's an odd function. An example of an odd function is y equals x. Graph of y equals x is a line that happens to pass through the origin. This is a very poor drawing. It doesn't pass through the origin. Let me fix that. Odd functions are symmetric about the origin. And what makes them unique is that inputs give opposite outputs. So for example, if I change this to be x, actually using function notation, and we'll talk about, say, f of 1. When I plug 1 in for x, I get positive 1. F of negative 1, the input, I get negative 1, the opposite output. So that means that the notation for it is that if I use the opposite input in an odd function, I will get the opposite output. And or notice f of negative 1 equals the opposite of f of 1. F of negative 1 equals negative 1. This is the opposite of positive 1. And we could test other things. Say that f of x equals x cubed minus 3x minus 1 over x. Well, what happens if I use the opposite of x? So by substitution, I'm wondering really about this. Negative number cubed is negative. Negative 3 times negative x would be positive 3x. Negative 1 over negative x would be positive 1 over x. Every term is opposites. X cubed, negative x cubed, negative 3x, positive 3x, negative 1 over x, plus 1 over x. I've verified that my original function is odd. That means if I were to graph this, it would be symmetric